you had the y equals, excuse me, we had basically these two styles of graphing. I'm generically writing them out in terms of, I think, how the book did it. I believe they used AX, B, CX, and D in the other one. That's the one we did on Tuesday that obviously took us like 6 minutes to kind of go over. So pretty easy. The first one, if you recall, or actually, no matter what, with any rational function, whether you start dealing with the asymptotes, your vertical asymptote is always the zeros of denominators. Okay? So your vertical asymptote, one thing that always holds true for everything, your vertical asymptote is always at the zero of the denominator. Okay? That will never change. All right, that's one of those, no matter what it is, and all that, it goes from there. So on that first one we talked about, when you had x minus h, that was an easy, that was a term in and of itself, so we just had to write it out through there. Okay. The k value for the y equals, for the one on the left there, that was always your horizontal asymptote for this style. So it was, excuse me, horizontal. And over here, there's the differences. Your horizontal asymptote was in the fraction of a over c. Oops. And remember, the a and c, those guys were the leading term coefficients. Hopefully that vaguely rings a bell. I think after that, it was just a matter of picking points and going for it. Now remember, when you pick points, you're always going to pick points two to the left and two to the right of your vertical asymptote. Okay. So if your vertical asymptote's at -1, you'd pick -2, -3, 0, and 1. And that's how we set those things up. It didn't change from that. It was kind of the same process for both styles. It was some mental math. You saw that you had hyperbolas, things that went opposite directions, and if things were, I think there was one where we had, sometimes if you had that fractional vertical asymptote, it was more often on the style on the right hand. Sometimes if you're at, I think we had one that the asymptote was at 2/3, I want to say. The next number you would have picked would have been 1, and you guys noticed it was really, really close. It was hard to decipher where it was going from. That happens when you get the fractional asymptote, because the closer you are to the asymptote, the more skewed you're going to wind up being. Yes, ma'am? Yep, because x equals is your vertical. Excuse me. And we went from there. So let's see here. I think I had. Nope, I did not. I hope. Did you guys have a nice break? I'm sorry. I'm sick at the very end of break, so it sucks. You didn't eat enough food. You weren't trying hard enough. So, for example, let's just do a couple of these real quick, just to remind ourselves. So just a quick walkthrough to remind ourselves of how this looked. Excuse me. I guess the one nice thing is that I actually finally got to see Joker.
Was it good?
I would say it was probably one of the best films I've ever seen. It was just so well done. But then the next day, my wife and I watched The Irishman, Scorsese mob movie on Netflix. I had such high expectation for it. It was kind of disappointing. Which one? Oh yeah. We just didn't get a chance to get out there. The house started. Everyone started getting sick this weekend. It's great. Anyway, in this case here, remember, first thing you always want to plot. First thing you always can do is get your vertical asymptote. Where is your vertical asymptote going to be from here? 3 or negative 3? Negative 3. Okay. So your vertical asymptote's at negative 3. Where is your horizontal? Is it 2 or negative 2? Okay. So from there, you start picking your table. We have negative 4, negative 5, negative 2, and negative 1. And that'll help us get our boundaries of where things are going. Let's see, negative 4 times the 4 is negative 16. Negative 16 and 12 is negative 4. So it's negative 1/4 minus 2, so that's negative 2 1/4. Again, this is the one of the few occasions that I say that for writing things out, because we're trying to plot stuff, the mixed number kind of makes a little bit of sense because it's easier to see where things are at. So at negative 4, it's negative 2 1/4, so it's a smidge less. At negative 5, we have negative 20, and then negative 1/8, so it's negative 2 1/8. So this one is getting closer here. Oops, that just a bit. So my idea is that since it's less, it should be doing this. Let me do the same thing on the other side. So let's see, that's negative 8, so it's 1/4, so negative 1 3/4. We'll call that about here-ish. And then negative 1 7/8. And then that's obviously getting closer. So that's a good sign that you can kind of see how the numbers are doing that. And that's what that would look like. The fact that you have the funkier fractions in this case is just because you've got that multiplier with the 4 thrown on top there, and that's where that goes. Okay. Excuse me. Is that vaguely yes or no?
I forgot what is the 3
0 denominator. What makes the denominator 0? Because you can't divide by 0, so that will always be your vertical asymptote. And we'll try the other style real quick. And real fast, the other style. Same idea. First thing you're always going to plot is going to be your vertical asymptote. So you got to figure out where the 0 of the denominator occurs. So you set it equal to 0, add 2, divide by 3, you get 2/3. Okay. So the vertical asymptote was at 2/3. So we'll say, I should write that down. Horizontal asymptote. Remember, since this is the style where you've got the degrees are the same, top and the bottom, since you've got a variable in both spots, all you gotta do is just take leading term coefficients, and that'll be your your horizontal. So it's 9/3, otherwise known as 3. Okay. This is going to be the weird one. I'm going to want to pick 1 and 2 just because it's the next couple of numbers. Once I pick 1, it's just going to be skewed a little bit weird because you're so close to an asymptote. And then I'll pick 0 and -1. So we'll pick out, what do I say, 1, 2, 0, -1. So if you use 1, you get 10 over 1. Okay with that? Yeah, so it's 10. Not drawn to scale. If I use 2, we got 18, so we got 19 in the numerator. 6 minus 2 is 4. 19 fourths is almost 5, isn't it? So 4 and change. So this is giving us the appearance it's doing this. And then we go through the other one. At 0, it's really easy. At -1/2. And then at -1, -9 plus 1 is -8. -3 minus 2 is -5. So that's 8/5, which is 1 3/5. So it's giving this appearance here, which is good. That one should be higher than the one at 0, because they have to be mirrored images of one another to make it work. Then we go from there. If you left it as 8/5, that's fine. This is that, like I said, there's a time and a place for mixed numbers, and this is one of those places that it works out okay. All right? Yeah. All right? What? Not good. 'Tis the season. You can leave it either way. When I'm plotting points, I'll usually use a mixed number just because it's easier to count than it is to say 8/5. I would say, oh, that's just 1 3/5, so it's a little bit more than halfway after 1. And in my mind, that's a usable place for mixed numbers, whereas you can't multiply or add with mixed numbers. It's a pain in the butt. It's just preference. So being able to do all those then gets us to the next style. And the next styles, there's going to be, what is there? 4 of them? I think there's about 4 different methods of the graphs depending upon what type of function you get, or what kind of rational function we have. But one of them that shows up pretty regularly, it deals with, and I kind of alluded to this earlier, it deals with going back to long division. Remember when we talked about that briefly when we did long division, what was that, about a month ago or so? Excuse me. And I said that long division, we didn't use it a ton when we were working with polynomials because it was easier to use synthetic when we were working with zeros and stuff. And that there was a time and a place for polynomial long division. This is the time and the place for polynomial long division. What happens here is that using polynomial long division for some of these rational functions is going to allow us to get what's called a slant asymptote. Okay. Now, this is one of the special cases that we'll see, but what I wanted to do today was just kind of just solely work on the long division portion before we got into all the graphing parts of it. Just because, I mean, it's not super there all the time, but it is something that we need to practice on. So let's go back and see what we remember about, actually we do this one first because it's easier. Let's go back and see what we remember about doing long division. Now, when you're dealing with long division, if it's a third degree polynomial, how many terms should it have? 4, okay? If it's missing a term, what do you have to put? a 0, okay? A placeholder, okay? So x cubed plus 5x squared minus 2, is it missing one of its terms? Yeah, what is it missing? The x. So as I write this down, I'm going to write x cubed plus 5x squared plus 0x minus 2 divided by x plus 4. Okay? Remember, the reason that we're doing that is so that way we have what's called a placeholder, and it'll allow us to line things up cleaner, if you will. The trick when we dealt with the long division is that we were kind of trying to figure out ways to eliminate the first term underneath the divisor, which meant that you had to figure out what do you multiply x by to turn it into x cubed, x squared. Good. Now, if I'm going to multiply it by x squared, I'm going to put it above the x squared. The other reason that I put it above the second term is that, notice there are two terms here. How many are out here? There's a coincidence there. Okay. Which means now I just distribute that x squared to both the x and the 4. So I get x cubed plus 4x squared. Now, we were saying we wanted to eliminate, which means I need to subtract both of these pieces. Remember, when you're doing this, please make sure you put subtraction symbols for both of them so you don't forget. Use a little bit of extra space in the paper. Paper is cheap. You've got plenty. And then you subtract. Your x cubes go away. And then you have 5x squared subtract 4x squared, and you're left with x squared. And then we bring down our next term. Okay. Now, when you multiply x by, you turn it into an x squared. X. Is it positive or negative x? Positive, good. If this was a negative x squared, what would I multiply it by? Negative x, good. Again, distribute through. And then we subtract twice. 0, and this becomes negative 4x. And then lastly, we bring down our minus 2. Okay. Excuse me. And then what do I multiply x by to turn it into a negative 4x? Very good. Bring that over. We have negative 4x minus 16. Subtract. And then I'm left with 14. Okay. Now, that 14 is a remainder. Okay. Is that 14 positive or negative? Positive, good. So my final answer would be all of that plus 4 over x plus 4. That's how you write the remainder. Sorry. What do you mean? Yeah, it's just, if you didn't have a remainder, that meant that x plus 4 was a term. You could have factored it out. But in this case, this is a remainder. It's not a term. It doesn't work clean. For today, for right now, nothing. You're done. That's just long division. Okay. Yes, sir. Then it would have been minus 14 over x plus 4. Remember, you guys have done this. You guys have done this before. If it was 3 goes into 17, how many times? 5. You used to write R2, didn't you? Yeah. Now, know that this is, it's just a fractional amount. Okay. What's that? Yeah. Yep. Our son Connor they're doing long division right now, and he's writing remainders, and it just kills me that he's writing an R. I'm like, dude, it's a fraction. And I just want to say something, but I can't.
That's how it's taught.
I know.
Like, if I'm gonna have kids, I'm not gonna learn something that they're gonna learn and then change like later on.
Yeah,
So,
it's
like, don't make them change.
it's really interesting when you go when I go to when we went to they had conferences last week, and my wife and I are both being teachers. Their teachers know that we're teachers, so they know that they're doing stuff at home a little different, and they're like, yeah, because we know upper level is going to do certain things. So anyway, does this vaguely ring a bell? All right. What was the degree of this one? Third degree. What's the degree of what you're dividing by? First degree. Okay. Now let's try this one. I didn't want to throw the one with the leading term coefficients at you right off the bat. I figured at least slowly ease your way into it. Remember, as you're writing this out, I would just write it out as what the long division would look like right away. Most textbooks and things, they write it horizontally. I have no idea why. It's just how it is. Okay. Third degree polynomial should have 4 terms. Does it have all 4 terms? You don't have to worry about any placeholders then. Good. So 2x plus 3. And then you just start going through. To turn a 2x into a 2x cubed, what do you multiply it by? X squared, good. So we just start lining it up. Distribute through. The 2's go away. -7 minus 3 is how much? -10, good. Yeah.
What if there's not like a thing like that first like can't just go away?
You would have to use a fraction. So, for example, if this was, let's say this was x cubed, I would have multiplied by 1/2 x squared. Does that make sense?
Yeah.
You can still do it with the fraction though. You don't see it very often, but it is possible. It is possible. Now when you multiply 2x by it, it turns into a -10x squared. Let's bring that around. And then we have, what is that, -17 plus 15, so it would be -2. And when you multiply 2x by it, it turns into -2x. 1. And there is no remainder. Very good. Which meant that 2x plus 3 was in fact a term of that. Okay. Excuse me. All right. Now, where this really is going to come into play for us more is when our degrees what are the 2 degrees that we're what's the degree of what you're the divisor? Is that the right one? What's underneath the symbol? That's the divisor, right? Was that the dividend? I don't remember. Thanks. I don't. You're dividing into. Hey! What's the degree of what you're going into?
Whoa.
The 3. What are you dividing by? What's the degree of what you're dividing by?
Divisor is outside the house. Dividend is inside.
Quotient. Quotient. I like outside the house though. I like that. What is it?
The divisor is what you're dividing by.
Will you throw me that marker, please? I'll bring some money. What is it?
So, divisors outside,
Divisor.
then dividends if they're done is inside, and then quotient is on top.
They've been
I thought there was something missing. All right, thanks, sir. Anyway, what's the difference between those degrees? Anyway, this is where this is going to come into play. When your degree of the dividend is one more than the degree of the divisor, this is where we're going to wind up with what we call a slant asymptotes. Okay? Then you won't have a slant asymptote. Okay? What's that? Regular horizontal and vertical asymptote. The slant asymptote occurs when your degrees are separated by 1. Okay? And it has to be, think of it this way, guys, think of it this way. This would look the exact same if it was written like this. Do you agree? That means the same thing? Okay. Notice the degree of the numerator is 3 and the degree of the denominator is 1. Since they're separated by 1 degree, this is the case for rational expressions or rational functions where you could have what's called the slant asymptote. All right. The other styles, you won't, but this is why we do this long division. So again, we would do the same idea: x cubed 2x squared minus 2x plus 3 divided by. Now, in this case, I have x squared plus 0x minus 1. I still need to put a placeholder there. We put placeholders no matter what, whether they're in the house or outside the house. I've never heard of it that way, but that was a really good way to put it.
I remember that in 3rd grade.
That's awesome.
Yeah.
I was surprised.
Everything back there.
I mean, I didn't remember 10th grade.
Crazy.
All right. So to start off, what do you multiply x squared by to turn it into negative x cubed? Just negative 1x, right? Bring that across. Oh, sorry, that should be a squared. Okay. Everybody with me okay on that?
Yeah.
Subtract everything through. So those go, this becomes 2x squared minus 3x, and then you gotta break down the plus 3. And now what do you multiply x squared by to turn it into 2x squared? 2. Bring that across. And this would have been negative 3x plus 5. And that was your remainder. Remainders, again, get brought back up. And I would just write it as x squared minus 1 as the denominator. You don't have to put the 0x there, and that's what they're doing. Now, here's what actually this gets you. I'm not really going to have us graph this today, but if you've got your calculator, put this in as a fraction bar. Look at my calculator out here. What was it again? Alpha y equals, then we had negative x cubed plus 2x squared minus 2x plus 3 over x squared minus 1. Now, let me change my window up a little bit here. If you did this, your graph kind of looks something like this. Okay. Now, obviously, there's some funky going on in the middle, but notice the two tail ends. Now, what was your quotient without the remainder? What was the equation that you got? It was what? Negative x plus 2? What are your y equals real quick? And put it in the next graph, negative x, you said plus 2? Now graph it. That's a slant asymptote. Something funky is going on, okay? What's happening here is, and this isn't something that we're doing, we're not graphing this one today, but we will graph this one tomorrow, is that when we get to our degrees being separated by 1, this first portion less the remainder is going to be the equation of what we call the slant asymptote. So there was a slant asymptote occurred at y equals negative x plus 2. All right, that's going to help us guide the graphing of these problems. Okay. This one's a little bit weird because you'll notice the denominator here. This guy had zeros at plus or minus 1. So in the graph of that, in the graph of this one, you had asymptotes at plus and minus 1. So as you would have picked points on either side, since there were 2 asymptotes, you would have had 2 points on one, 2 in the middle, and 2 on the other side. So you would have had 6 points for something like this. So that's how you would have been able to see all these different curves going through. Okay. The 0 being at was it negative 3, I think, is your last term coefficients on there. So you get those little points that make it work. Plotting it and looking through it doesn't change. It just takes an extra minute or so because of the double asymptotes. Okay. The slant allows us to figure out how much that curve comes back up. That's where it comes from. All right. That's why I wanted to spend time today going back over long division, so that way you guys, when this case does show up tomorrow, you're not going, hey, how do you do that again? Because sometimes you guys do that. What's that? No, you won't do that as much. So I made a quick little What's that? Well, you have to know how to use them to get slant asymptotes. So, yes. You should be able to knock this out. All right. Ladies and gentlemen, come on. In this case is in here. What I was doing was, it doesn't appear as though I don't see anything that needs extra placeholders. I kept things pretty straightforward as far as your divisor. Yeah, this shouldn't be very difficult at all. It's just practice on how to set it up. I have an answer sheet. I did not post it yet because I just ran it off this morning, but I will post the PDF file with the solutions for the remainders and all that stuff on there for you guys. It'll be on the calendar later on today. Okie dokie. Okay. Okay.